Hello, I'm Bob Palmer, Executive Director of the Advanced Radar Research Center here at the University of Oklahoma, also a professor in the School of Meteorology and Associate Vice President for Research and Partnerships. So in my roles here, I lead the ARC, the Advanced Radar Research Center, in our main goal of designing, building, fabricating, and testing and fielding advanced radar systems for a variety of applications. Our origins are in severe weather, but we also apply our skills to other applications from automotive radar to biomedical sensors to DoD applications. So today you're going to see our facilities, including very advanced electronic systems that test our designs, but also facilities such as the anechoic chamber, our microfabrication lab. A lot of 3D printing is going on nowadays to help us quickly field radar systems. And then finally, we're going to show you some of our mobile radar systems that are used for field experiments, looking at severe weather and other type of scientific applications. So please enjoy yourself, and I hope you have a great time today at the National Weather Festival in 2020. Thank you.
Hi, I'm here in the Radar Innovations Lab lobby area, and behind me is a tornado simulator. So in the lobby we have a lot of different demonstrations of things that we are doing in the lab. So we do a lot of tornado research. We also have here a Smith chart, which is it's a diagram commonly used in electrical engineering. Okay, so we're in the main part of the Radar Innovations Lab, which is the area where we have the students and faculty work on various projects. These projects range from building radar systems and designing the radar system to taking out the radars after we've collected the data, or taking out radars to collect data and doing analysis of the data for scientific research to improve weather forecasting. So many of the students that you'll see down here, some of them are engineers, some of them are scientists, but they're working together on many interdisciplinary projects.
Hello, my name is Hjalte Sigmarsson. I'm an associate professor here in electrical and computer engineering at the University of Oklahoma and a member of the Advanced Radar Research Center. We are here in our fabrication laboratory, where the goal of this lab is to allow us to be self-sufficient in prototyping components and systems. And a good example here is this radar system next to me, where this was completely made in-house. This is a project that we worked on a few years ago. We made the printed circuit board here for the antenna. We made the entire feed assembly is 3D printed, which makes it slightly unique. And this particular antenna is an antenna that we call a reflect array. It's a flat antenna that emulates a dish, and it allows us to mount our system on the back, and we can have the entire radar housed in this little radome here. And what's really cool about this system is that we 3D printed this entire feed assembly, including these antennas. These antennas are 3D printed out of plastic and then plated with copper. And we tested this here in Oklahoma. We ran it outside for an entire summer, and the plastic pieces were just great. And so one of the things that makes us unique here at OU is that we are involved in pretty much a full innovation cycle. We go from brainstorming and idea generation, we go through the math and the theory for our designs, we run simulations, verify them on the computer, we come here to the lab and we fabricate our designs, and then we take our designs and we field them for going out and doing science missions. And one thing that makes us unique is that we offer our students the opportunity to be involved in any or all aspects of a full product development cycle. Okay, so part of being self-sufficient is to make our own printed circuit boards. And for that, we have several processes. We have a mechanical milling machine, we have photolithography, and we have a laser milling machine. And this laser milling machine is actually a really nice tool for us to have, and it allows us to do features on printed circuit boards down to about 25 micrometers. Here's an example of a printed circuit board that was made on a thin substrate, and it does just a great job of doing that. And this is something that would be hard to mill with a mechanical milling machine, but we're able to do it with the laser with ease. Also, this laser can do ceramic circuit boards, and we can actually cut ceramics with this, which actually makes it a really nice tool to have in a lab.
Hi, this is Jorge Salazar. I'm assistant professor at OU. And this is the Advanced Radar Research Center. I would like to show you two important facilities that we use for measuring antennas. This is an antenna, and this is a state-of-the-art phased array antenna system. When we decide these antennas, we need to test it. We need to have a place like this to do testing of antennas. So here, for example, we have a UAV where we put an antenna here and we use for sensing. So when we need to characterize antennas like this or like this, we need to have this kind of facilities. So this specific chamber, they measure antennas from 800 megahertz to 18 gigahertz. So as you can see, it's quite big. This chamber is nothing else than a metal enclosure with some special absorbers that enable us to suppress the reflected energy in the walls because it's a metallic structure. So in this side we have a probe, in this side we have the antenna. This is an antenna array that we use for radar applications. So we measure the electric fields directly in this chamber without a need of doing any signal post-processing for extracting the characteristics of the antenna panel. On the other side, we have a different chamber. It's a little bit more sophisticated. And this chamber is called near-field system. The reason that we call near-field system is because we're measuring the antenna panels using the near-field region of the electric fields. So, of course, for doing these measurements in a short distance, we have to have a robotic system that enables to move precisely the probe in front of the antenna. So let me show you what I'm talking about. So this is an antenna, and this antenna, when it's excited, it transmits a signal that we cannot see with our eyes. We need to have a special equipment, a special system to visualize these fields. So, for example, this is a antenna parents or the electric fields of a dish antenna. So this antenna provides a narrow beam, a pencil beam, and with this pencil beam we can visualize the electric field. You see that we can have different cuts, or we can measure the near field and the far field without any problem. And you will see the beautiful antenna pattern here that represent the energy focused in one specific position.
Before we start the mobile radar tour, I'd like to give you a bit of an overview about radars across the United States and how our research fits into the broader picture. The operational radar network is called NEXRAD, and this is a network of 159 radars across the United States. And these data are used by National Weather Service forecasters, and also what you see on your weather app when you look at radar images there. While the NEXRAD radars provide high-quality data across the country, one of the key limitations is that they require 5 minutes to scan a storm at multiple heights. So we are generally left without a complete picture of how tornadoes form, since this tornado-producing storms will often change much faster than over a 5-minute period. Some tornadoes don't even last for 5 minutes. So we need radars that can scan much faster than this to be able to detect all tornadoes and see how tornadoes are forming. In addition to that, most mobile radars also require several minutes to scan full storms. So one of our goals at the ARC is we want to develop next generation technology that can allow us to scan much faster. So one of the types of radars we'll be showing you on the tour are called dual polarization radars, or dual pol. And this is a radar that transmits and receives radar waves that are both horizontally and vertically oriented. So the advantage of that is when you transmit a wave that's horizontally and vertically oriented, we get different types of signatures back from the horizontal wave and the vertical wave for different types of precipitation particles. So hail or rain may send us a different signature, and this gives us additional information about the types, sizes, and shapes of these different radar targets. One example of this where this is useful is for tornado debris. This on the bottom right, there's an example. This yellow color area here is debris that's been lofted by the tornado, so we can remotely detect tornadoes with the radars. And NexRad was recently upgraded to dual polarization technology across the country. That occurred between 2011 and 2013. Another important type of radar is a phased array radar. And this is a radar comprised of many different small antennas. And the signals from these are combined to produce a radar beam that can be steered without physical movement. So current radars must rotate a dish around mechanically, which takes a long time. So it can take several minutes to complete a scan. But a phased array radar can change the beam position almost instantaneously. Phased array radar technology can address the slow scanning limitation of NexRad. So it makes it possible to scan all of the storms around the radar at many different heights in a minute or less. One of the challenges that we have going forward is combining phased array and dual pol technology, since this will be important for an NexRad replacement network. So many of the radars that I'll talk about today that are coming in the future are phased array radars that are also dual pol.
Hi, I'm David Bodine. I'm a research scientist in the radar group here at OU. This is our high bay where we keep a lot of our mobile radar systems. These are radars that we take out to storm chase and study severe weather, as well as do a variety of other projects to monitor flash flooding, even studying things like the migrations of birds and insects. So I'll take you through a tour of our mobile radars. Many of these are radar systems that we use for science, but also are prototypes of radars you might see across the country in the next 10 to 20 years. Okay, this is our PX-10000 radar. It was built in a partnership with private sector companies. So some of the radars that we have here, we've worked with private companies who take the technology that we've developed in partnership with them, and then they are able to market that and sell it across the country. So this is one of those systems. It's a radar that's on the back of a trailer, so we can take it to a lot of different places and leave it for long periods of times. What's unique about this system is it's a rapid scan radar, so this pedestal can rotate around in a circle in 1 second, so it's really fast. So if you want to scan at 10 different heights, you can get 10 different heights in only 10 or 20 seconds. So it's really quick. The other unique thing about it is it's a dual polarization radar. So this radar transmits radio waves in both the horizontal dimension and the vertical dimension. And using the signals that you get from both of those dimensions, you get more information about raindrops, you can identify tornado debris and hail, as well as a look at a variety of different things with the system. This is the Raxpol. This is one of our mobile radar trucks that we take out storm chasing to collect data on severe thunderstorms and tornadoes. We've also taken this radar out to collect observations of just general weather as well as hurricanes. This radar, the unique thing about it is this dish rotates 180 degrees per second, or once every 2 seconds it can do one level of the atmosphere. So then it can cover multiple levels of the atmosphere in about 30 or 40 seconds. So like the radar, the PX-10000 radar that I showed you earlier, This radar is also dual polarization, so you can get a lot of information about where there's rain, where there's hail, where there's tornado debris. In addition to that, the future radars are expected to be phased array, which will scan really quickly, but also dual pulse. So this mobile system gives us a view of what that might look like in the future with really fast scanning capability. So I'm going to go ahead and change this radar from the slow scanning mode to the fast scanning mode. So this is the scanning mode that this radar uses when we're out storm chasing. When you want to see things as fast as possible, the radar will spin gradually up in height, and we'll get a look at different altitudes in the storm very quickly. And we'll get an entire view of the storm in about 20 seconds. So the types of radars we're developing are called phased array radars, which are the next generation type of radar designed to replace NexRad. So one example of that is up here is a cylindrical phased array radar. And this radar, basically there are strips of antennas that go all the way around in a cylinder, and then we can point in all different directions almost at the same time to where we can scan really quickly. So this radar is capable of getting volume scans in 1 minute or less. In addition to that, we're developing a couple of other radars, one's funded by the National Science Foundation called PAIR, or the Polarimetric Atmospheric Imaging Radar. And PAIR is going to be a rapid scan system we can take out in the storm chase, and we can collect observations of tornadoes, severe thunderstorms in 10 seconds or less. So you can get a really good look at how quickly storms are evolving with a lot of detail. In addition to that, we're developing a HORUS system, which is an all-digital phased array. And this all-digital radar is basically like 1,000 little mini radars all in one system. So it gives us really fine control, so we can do a lot of different scanning modes all at the same time to scan really quickly. And it also gives us an opportunity to get much more accurate measurements than we would with existing radars today.
Hello, I'm Sam Emerson. I'm a second year's master's student here at the Advanced Radar Research Center at the University of Oklahoma. What I'm holding here is a passive radar antenna for the Bistatic Radar project here at the ARC. What this project involves is a network of low-cost passive radars that essentially allow us to sense radar signals from existing radars. Now normally, an existing Doppler radar would only be able to see winds coming towards or away from that radar site. However, with these radars, we're able to get multiple perspectives on the wind field, which allows us to retrieve the entire three-dimensional wind field, as you can see here. This type of data is extremely useful for weather forecasters. In addition, these radars are extremely low cost and are able to augment our existing radar system at very little additional cost. In addition, these radars can also be used with any future phased array radars, which will be extremely advantageous.
Hi, my name is Rachel Cross, and I'm a second-year master's student here at the University of Oklahoma. For my research, I'm using a dual-pole radar simulator called SimRadar that was developed here at the Radar Innovation Lab. Using this simulator, I'm looking at what we call a tornado debris signature, something you can see developing right here. Basically, this is just a signature on radar that tells us that debris has been lofted by an ongoing tornado. Specifically, I'm interested in how different debris types, sizes, and shapes affect how this parameter looks on radar. Now, these different differences could range from how high the debris is being lofted by the tornado to how different variables, things like you see here, change depending on what type of debris is in the tornado. Now, a good example of some of these differences come from comparing leaves to wood boards. This is illustrated in these figures right here with these dual pole variables plotted. Here you see with the leaves, generally they have higher values with the wood, compared to the wood boards that have lower values. Hopefully, by quantifying these differences, we can relate what we're seeing on radar to the damage that's occurring in real time.